And this capacitance will lead to like essentially a dipole-dipole coupling between the two qubits. That means these two qubits will see each other. What they did and how they, in fact, it's how they perform two qubit gates in this system can be understood with this plot here. The idea is that they take this transition, which as a function of, this is basically the frequency of one of these qubits, so they fix the frequency of one qubit, and they bring the frequency of the other qubit very, very close, but not resonant. They bring it close, such that it's this trajectory they plot here. At this point, even though it's not resonant, already the eigenstates of the system are superpositions between the two qubits. So this initial state, they have to do this fast but adiabatic, but this initial state acquires a phase as it travels towards this point, and then it comes back. So, and then this phase depends on the state of the other qubit. This is called the control phase gate. It's actually here. In fact, this is the CZ, so that's when this phase is pi, and then it's 1, 1, 1, minus 1. So this matrix is telling you that if the control qubit is in 0 state, then I do this operation, which is identity. If this control qubit is in the 1 state, then I do this operation, and that means I flip the sign of my second qubit. And this is the control phase gate, or control Z gate in this case. So this phase is universal. That means that any 2-qubit operation can be built with this gate and then single qubit rotations. So that's universal. That means you can perform any quantum algorithm using this gate. And this gate is quite natural in the superconducting circuits. So this control phase. The one I explained before, the swap itself is another gate, but the swap is not universal. Half swap is universal. The square root of swap, that one is universal. So you can also do universal quantum computation with this resonant interaction. Only that one is more tricky to control accurately. This one seems to be very good because they're able to demonstrate gate fidelities which are better than 99% for 2-qubit gates. And this is better than what people can do with ion traps. So that's already a remarkable result. And they are fast. They're under 100 nanoseconds. Single qubit rotations, they are a few nanoseconds. So taking into account that this qubit's lifetime is about 50 microseconds, so you have a lot of time to perform lots of operations. So the natural question is, what do you do with so many qubits? And what they did is a simulation of the Hubbard model. In particular, they were looking at simulating fermion scattering. That means 2 electrons that scatter in a potential well of this lattice. In that particular experiment, they used up to 4 qubits, and basically there's a mapping. So qubits are actually not fermions, so you cannot directly pretend that the qubit is a fermion. It doesn't follow Fermi statistics, but you can fermionize a qubit by using a method where essentially the low, so you can basically map fermionic operators with qubit operators, and this is a well-known technique, theoretical technique. Is a bosonization or fermionization, either way. And with this technique, they were able to map fermionic operators with multiple qubit operators. And in this way, they were able to simulate the evolution of this scattering. So this is what they were trying to simulate, essentially the exchange of the population between the two wells. And this is their simulation. You can see that as a function of the number of steps of their simulator, they were getting closer and closer to the ideal. I mean, eventually they got this far. It's not exactly this, but this is consistent with the single error of every gate, which is caused by the decoherence of the qubits. In the longest sequence, this involved about 1,000 gates, and this is definitely the longest sequence that any system has tried to do to perform a quantum simulation or a quantum computation. So this experiment was quite remarkable. This is an example of what these traces look like. So these are like the pulses, the microwave pulses that are sent to these qubits. So these bumps here, this is frequency shifting, and these bursts, this is qubit state manipulation. And so they basically were performing this for the 3 qubit mode. They were performing this set of gates, and then they were just repeating this over and over. And every step here is a repetition of this sequence. And this whole sequence is this here, which lasts for about 1.5 microseconds. So you see this is getting already quite complex. But that's the way to go to perform quantum simulations. This is an actual, this is technically called a digital quantum simulation, because what they do, they take the Hamiltonian of this model, and then they break it down, like they perturbatively approximate it in time. So they basically simulate in time steps this model, like in snapshots. They've also simulated the icing model using the same device, and they also had similar results, the same group.
So,
yeah.
Is it possible to identify the bottleneck in this calculation? So why is the error so large compared to the ideal case? Is it because of the readout errors, because of the single qubit?
Yeah, even like a 99% fidelity, when you have to repeat it 1,000 times, it adds up. And they demonstrated that this infidelity here is consistent with these so many gates. So it's simply the accumulation of the errors. So it's just a long sequence. There's no error correction. I mean, ideally, the day you have error correction, these two will be identical, but then you will need to correct for these errors. But this is raw, so that's what you get. Still, it's good that it works. This is another 2-qubit gate that I wanted to show. This is from the IBM group. This one is a gate mediated by a resonator. So here we have 2 qubits, qubit 1 and qubit 2, and in between they're connected by a resonator. As I didn't go into the details of that, but when you have 2 qubits coupled to a single resonator, and there is a direct interaction between the qubits mediated by the resonator through virtual processes, even if these qubits are far away from each other. And so what they did in this experiment is a bit more complicated, because this resonator had a squid, so they could actually change the resonator frequency fast. And what they did in this experiment was to have the 2 qubits at a different frequency, so with a finite detuning. And then they applied fast pulse in the squid to change the resonator frequency fast. And they made this change of the frequency to match exactly the frequency difference between qubits. And in that way, they were basically inducing qubit swaps. So you see yellow is qubit 2, and blue is qubit 1. So this was essentially the qubits being swapped through the resonator, through this driving, essentially mediated by the photons coming from outside of the resonator. So there's actually many other schemes that people have come up with for 2-qubit couplings, but so far these ones are the ones that are being used at the moment. Another example of what people have been able to do, it goes into a category of algorithms, which is rather modern, I would say, which is a hybrid type of algorithms. It's a hybrid between classical and quantum. And these are known as variational quantum eigensolvers. So variational eigensolvers may ring a bell from your days at undergrad when you were studying like quantum mechanics and methods, approximate methods to solve Hamiltonians. So this is one step beyond, and this uses some quantum processor to complete part of this calculation. So the idea is that you have you want to calculate something, you want to, I don't know, diagonalize some Hamiltonian, and there is one step that requires you to estimate the energy of the system. And in order to do that, then you call a quantum processor. And this quantum processor, you perform some, in fact, this is almost like a kind of random set of gates, and this produces an estimation of this parameter. Then this estimation you plug in into your classical calculation, and then you repeat the cycle. And then you do this over and over until you converge to the solution of the problem. So the IBM group, they did this with 6 qubits. You see this is qubit 1, 2, 3, 4, 5, and 6. And the wiggly line here is the readout resonator for each qubit. So the qubits are these parallel paths. This is the capacitor of the qubit. And then each qubit had its own driving lines and also its amplification chain. So this is, you see, the complexity grows up very fast. And what they were able to demonstrate was essentially calculating the bonding energy of some molecules. These are still trivial molecules for chemists, but nevertheless, this was like a proof of principle that this method works. So the first one was the hydrogen molecule. This has been already calculated with other quantum systems, including photonic chips. This was the first demonstration. But so here, what I'm plotting here, this is the interatomic distance between the two hydrogen atoms. And when you put them very close to each other, there's a strong force that they repel each other. And then as you separate them, there is a stable point where the molecule mostly resides. And then as you separate them even more, at some point it breaks. So this energy is what the chemists are very, very interested in, this dissociation energy. They did the same calculation for the lithium hydrogen. This one was done using 2 qubits. This one was performed with 4 qubits. You see, this one is a bit more complicated, and the results are not, this is the exact solution. So it's coming close, but it already has a little bit of deviation. The largest molecule was performed with 6 qubits, is the hydrogen beryllium. And you see that already this one deviates a bit more. Again, this is caused by the inefficiency of the pulses and the coherence of the qubits. But this is this way to go to simulate bigger and bigger molecules to start to understand more complicated problems, like the Haber-Bosch process, which has to do with capturing nitrogen for fertilizers, for example. All right, I'm at the last part of this talk. This is going to be fast. Where are we now, right now, in the world, in the quantum computation with superconducting devices? So this is only the progress of the group that has done most in this direction, which is the Google/Santa Barbara team, the group of John Martinez. So in 2013, they set the record at 5 qubits. You can see them, 1, 2, 3, 4, 5. Readout resonators. This is this fit line, a single line that can talk to all the resonators, and then a signal goes out. And then these are all these local lines for each qubit. You start to count how many lines this means. Then 2 years later, they measured like a 9-qubit device. This is the one they use for these quantum simulations that I described. And again, you see the readout resonators, the control lines. Last year, they were showing at a conference, this is not published, but they have a 22-qubit device. So this is 2 rows of 11 qubits next to each other. And these are all the control lines on both sides. And right now, they are already working on a 72-qubit device. You cannot see here because they don't want to show it. I think when they took this picture, there was no device, but they just wanted to kind of like show off. Basically, what they're trying to do at this point, they try to demonstrate what people call quantum supremacy, or in Europe, people prefer to say quantum advantage because supremacy has strange connotations. And the idea is that you want to demonstrate that with your device, you can perform some operation that you cannot reproduce with a supercomputer, even the best supercomputer in the world. And the Google group have some idea of basically calculating the entropy of the system of 72 qubits after a sequence of random gates. And these random gates will put this massive qubit device in an entangled state, which will have a large entropy. And because in a standard supercomputer, like I described yesterday, more than 50 qubits is a no-go. Supposedly, for this operation, the supercomputer will give up. And that will be the point where quantum computation is the winner. But so this is going to happen maybe this year, maybe next year. So you will probably hear it in the news. It's not only, not everything is happening at Google right now. Fortunately, there's more. IBM has been allowing external users to control some of their devices with the IBM Quantum Experience. This has been a very successful platform because anybody can just log in, send some code, and this runs their machine. They have two, right now they have one of 5 qubits and one of 16 qubits. Here, this is the 16 qubit device. There is this other company called Rigetti. So he was an employee of IBM and he went to Silicon Valley and raised some money and started a company which has been existing for about 2 or 3 years now. And they are 100 people, so they're growing very fast. And last year they published one of their first papers with many qubits. So this is a 19 qubit device with which they demonstrated some kind of machine learning procedure. And this one is also available online. They also have the option for you to go in and run code in this machine. So these are the largest endeavors in building big devices. So you need a lot of people, a lot of resources, and a lot of funds. And this is why it's happening in private places and not at universities anymore. Universities, there's a lot going on, but it's not related so much to scaling up the devices. Okay, I'm just going to skip that. And this just have a minute to talk about this one because I think this is one of the best outputs of the field. As I mentioned before, all the readout of qubits is now performed using this quantum limited amplifier. And these amplifiers consist of superconducting devices. The latest one is this traveling wave Josephson parametric amplifier. You can see the device here. It's essentially a waveguide, but it's built of a series of junctions. And there's on the order of 2,000 junctions in a row. You see this is a zoom in of the input and one of these blocks. So these are niobium junctions. It's a tri-layer process, so the junction is like in the vertical direction. And you see this object here. This is essentially a resonator that kind of like corrects for the mode mismatch in this waveguide, because there is some mismatch in the modes if you don't add this, in order to produce amplification. So the way this works is that you pump your system, so you send a strong tone at a certain frequency, and this tone basically propagates and gets out of the chip. And then if you come with your probe tone, because this is essentially a nonlinear medium, there is energy exchange, and energy from the pumping tone goes into your probe tone, and your probing tone is amplified. And they have demonstrated a gain of over 15 dB for a 7 gigahertz span. So this is amazing. But what's really amazing is that the noise of the system, as they pump it to an optimal point, is less than 1 photon. So less than 1 photon is very, very close to the quantum limit. So quantum mechanics imposes a limitation in amplification in linear amplifiers. So this is actually a very peculiar result that is actually all comes from Heisenberg uncertainty principle. And the quantum limit is half a photon. So that means that no linear amplifier can amplify a signal without adding half a photon of noise. The best commercial amplifier, if you are familiar with them, this is Hempt amplifiers at 4 kelvins. This adds about 40 photons, 30 to 40 photons of noise on average. So this one only adds like 0.94. So you see, if you put this amplifier as your first step of your amplification chain, you gain a lot of signal. And that's how these measurements can be so fast with qubits. And you can do these feedback processes. So, of course, this is a standalone chip. I mean, this thing will start to be sold in companies very soon. So this is a direct product of this field that will benefit many other areas. And so, final slide. My prediction. I mean, that's my prediction that in the next 5 years, as I said, we're going to first see this supremacy or quantum advantage, and then the optimization problems will start to be applied to real cases. Then we will go into the simulation of small, but not that small that you cannot simulate them in a supercomputer. And finally, we will get into this error-corrected quantum computation. And from this moment on, is uncertain. But the point is that there's so many applications that are not known today because quantum computers so far have been something hypothetical, but they're becoming real. So as there's more users, more developers of quantum code, quantum algorithms, there will be many more applications coming up. And with this message, I'd like to thank you for your attention.